In this lesson, we will discuss pre-falling bodies. Take note, when we say pre-falling, it does not mean that the object is necessarily dropped from rest. It can be the object is being thrown straight upward or straight downward. Wherein when an object is in pre-fall, it will only experience an acceleration that is equal to the acceleration due to gravity, and that is the negative of 9.8 meter per second squared. The acceleration due to gravity is negative because the acceleration due to gravity is always acting directly downwards. And the formulas that we will use to solve for problems about pre-falling bodies is the same equations in the straight line motion, wherein we just change the acceleration of A to the negative of g. Since we use the negative on the formula, that is why the g here is just the magnitude of the acceleration due to gravity, and that is the 9.8 meter per second squared. And from a delta x as a horizontal change in position, we will change it to delta y. And before we solve for a problem, take note that when we say delta y, this is the vertical change in position, wherein it can be solved by the final position yf minus the initial position yi. And it is always very important that we use a reference frame in determining for the position yf and the yi, wherein most of the time, this is the ground or the initial launching point of the object. Then, the direction is very important, wherein when the object is moving upwards, the velocity is positive, and when the object is in on its downward motion, the velocity is negative because velocity is a vector and it has a magnitude and direction. On this video, we will solve three problems, and let's start with this problem. A stone is thrown from the top of a building, is given an initial velocity of 20 meter per second straight upward. The stone is launched 50 meters above the ground, and the stone just misses the edge of the roof on its way down. First, let's try to draw this problem. We have a stone that is initially 50 meters from the ground. Let's say that this is our stone, and initially this is a 50 meters from the ground. And this is thrown straight upward, wherein the initial velocity is equal to 20 meter per second. And of course, after a certain time, this stone will reach its maximum height. And after reaching the maximum height, the stone will momentarily stop and will start to fall. And based on the problem, that the stone will just miss the edge of the roof on its way down. And as we see, the ball will fall to the ground or will strike to the ground. And for our problem, we want to solve for letter A. Determine the time at which the stone reaches its maximum height. That is a time wherein the final position of the stone is equal to the maximum height. Let's say that the maximum height is equal to the capital H max. Okay? And take note, when the stone reaches its maximum height, at the maximum height, the final velocity of the stone should be equal to 0 because the stone will stop momentarily after the stone reaches its maximum height. And by that, we have here a given of a final velocity, an initial velocity, and we want to solve for the time t. And from that, we can use the equation of the Vf is equal to Vi minus gt. And our goal is to find the time t here. Let's try to solve for the t here algebraically. Transposing negative gt, that becomes a positive gt, is equal to Vi. Transposing Bf on the right side of the equation, that is minus Bf. Then divide both sides of the equation by g. And our time t now will be Vi minus Vf all over g. Then, let's now try to substitute all our values for the Vi. we have the initial velocity of 20 meter per second. And for the final velocity, that is a 0 meter per second, divided by the acceleration due to gravity, which has a magnitude of 9.8 meter per second squared. And solving for the time t now, this will be equal to 2.0408 second. And this will be the time for the stone to reach the maximum height. Then, for our letter B problem, we want to solve for the maximum height of the stone. That means this is a final position wherein this final position represent the maximum height that the stone can reach. Wherein we can apply the formula of the delta y is equal to VIT minus 1 half GT squared. Wherein we know that the delta y is the change in position, which is the YF minus YI is equal to VIT minus 1 half GT squared. Solving for the YF, which is our maximum height, that will be our Hmax, that is our concern, a final position wherein that is the maximum height of the stone. Just simply transpose this YI on the right side of the equation, that will be YI plus the VIT minus 1 half GT squared. Then let's now try to substitute our values for the YI. That is the initial position of the stone, wherein initially this is a 50 meters from the ground, that is 50 meters, plus the initial velocity of 20 meter per second. And for the time t, this is the time for the stone to reach the maximum height, which is 2.0408 second minus 1 half for the acceleration due to gravity, which is the 9.8 meter per second squared. And for the time t, that is a 2.0408 seconds squared. Just type this equation on your calculator, and therefore, the maximum height of the stone now will be equal to 70.4082 meters. And take note that this maximum height is measured from the ground, and this is 70.4082 meters above the ground. And this will be our final answer for the maximum height of the stone. Then for our letter C problem, we want to solve for the velocity of the stone when it returns to the height from which it was thrown. That means you want to solve for the final velocity wherein the final position of the object is 50 meters from the ground. This is the height wherein the object is being thrown. And solving for the final velocity, we have a YF, and we also know the YI. We can use the formula of the VF squared is equal to the VI squared minus 2G delta Y, wherein our VI is the 20 meter per second. We have the VI, and for our G, of course, that is 9.8 meter per second squared. And for the delta Y, this is a YF minus YI. Then let's try to substitute our values. This will be VF squared is equal to the 20 meters per second, then squared, then minus 2 multiplied by the acceleration due to gravity, which has a magnitude of 9.8 meter per second squared. And for our final position, this is a 50 meters from the ground, and the initial position, which is also 50 meters from the ground. And as we see, that the delta y is equal to 0 because there is no change in position vertically at all. Therefore, this negative 2g delta y will become equal to 0. Solving for the final velocity now on this equation, our final velocity will be equal to the square root of the 20 meter per second and squared. Take note that when taking the square root of a number, this is always equal to the positive and the negative. Therefore, our final velocity here will be equal to the positive and negative of 20 meter per second. Wherein, one of the answer here is correct and one of the answer is wrong. Wherein, our final answer should be the final velocity of negative 20 meter per second because we know that the object is in the downward motion at this position. That is why this must be a negative 20 meter per second. That negative indicates that the motion is downward. Then, for the letter D problem, let's go back with our question. For letter D problem, find the velocity and the position of the stone at a time of 5 seconds. Solving for the final velocity at a time of 5 seconds, just simply use the formula for VF, wherein this is a VF is equal to the VI minus GT, wherein we have the initial velocity of 20 meter per second, the acceleration due to gravity of 9.8 meter per second squared, and for the given time, that is a 5 second. Solving for the final velocity now, this will be equal to the negative of 29 point or the negative 29 meter per second. And the answer is negative because as we see from our answer in letter A, after a 2.0408 seconds, the stone reaches its maximum height. And after a this time, of course, the stone now will starts to fall. And at a time of 5 seconds, the object now is in the downward motion, and it makes sense that is why it is negative. And for the last follow-up question, we want to solve for the final position of the object or of this stone at a time of 5 seconds. Solving for the delta y, this is delta y is equal to VIT minus the 1/2 of g multiplied by t squared, and for the delta y, that is a yf minus yi is equal to VIT minus 1/2 gt squared. Transposing this negative yi, our final position yf is yi plus the VIT minus 1/2 gt squared. Just simply substitute all our values. The initial position of the stone is 50 meters from the ground, plus the initial velocity of 20 meter per second, multiplied by the time of 5 seconds, minus 1/2 the acceleration due to gravity of 9.8 meter per second squared. Then, for the time t of 5 second squared, just type this equation on the calculator, and you will get a final position yf as equal to 27.5 meters. And take note that this 27.5 meters is measured from the ground, or 27.5 meters above the ground. And this will be our final answer. Or you can also write the final answer in terms of a height that is below from the launching point. You can also express the answer to be 22.5 meters below the launching point, and that is 50 meters minus the 27.5 meters. Okay, and that's it for our example problem number 1. Now, let's try to have another example problem. For our second example problem, an object is thrown vertically and has an upward velocity of 18 meter per second when it reaches 1/4 of its maximum height above its launch point. What is the initial speed of the object? First, let's try to illustrate this problem. Let's say that the object is launched from this initial position, wherein let's say that at this reference frame, our initial position is equal to 0 meters, and the object is being thrown straight upward, wherein after a certain time, it will reach a one-fourth of its maximum height. And at this point, the final velocity of the object is equal to 18 meter per second. Then, the object will reach a maximum height of h. Okay, this is the maximum height of the object, which is h from the ground. And for this problem, we want to solve for the initial velocity of the object, that is bi. To solve for this kind of problem, what I'm gonna do is I will divide this motion into two parts, wherein I will divide it into the first part, wherein having an initial velocity of vi reaching to a final velocity of 18 meter per second, and that is at a position of h over 4 from the ground. This is the first part of the motion. And then for the second part of the motion, that will be a initial velocity of an 18 meter per second. Then, reaching the maximum height, this will have a final velocity that is equal to 0 meter per second, since the object will stop momentarily after reaching the maximum height. And as we see, we have here a given of a velocities, a final velocity, and then a displacement, wherein can be solved in terms of h. Let's use the formula of the Vf squared is equal to Vi squared minus 2g delta y, wherein using the first part of the motion, take note that our initial velocity here is bi, that is the unknown, and the final velocity here is equal to 18 meter per second. Then, for the final position yf here, this is equal to the maximum height over 4, which is the h over 4, and of course our initial position yi, that is equal to 0. Using this formula of Vf squared, let's try to substitute. We have here a Vf squared of 18 meter per second, then squared is equal to the unknown of the initial velocity squared minus 2g. And for our delta y, that is a final position yf minus the initial position of yi, which is 0, and that is h over 4 minus 0, or just simply equal to h over 4. And this is now h over 4, the final position yf, minus the initial position 0. Let's try to simplify this equation further, and you will get the equation of 18 meter per second squared is equal to the Vi squared minus 2g. Again, the h over 4 minus 0 is h over 2. Or I mean h over 4. Then, solving for the Vi here, we can solve for the Vi on this equation as Bi squared is equal to the 18 meter per second, then squared. Transposing this negative 2g h over 4 on the other side of the equation, that is a plus 2 over 4 is 1 half, and this will become a gh over 2. And to solve for the initial velocity Vi, just simply take the square root of this equation both side, and that will be Vi is equal to the square root of the 18 meter per second, then squared, okay? Then plus the acceleration due to gravity of a 9.8 meter per second squared multiplied by the maximum height h over 2. But take note that we cannot solve for the initial velocity using this equation alone, since we do not know what is the value of this maximum height h. That means we need to solve first for the maximum height h. And we can do this using the second part of the motion, wherein on the second part of the motion, we can say that the initial velocity on this part of the motion is equal to the 18 meter per second, and reaching the maximum height of h, it will have a final velocity of 0 meter per second, and for the final position, that is the maximum height h, and for the initial position, that is the position of h over 4 from the ground. Then, again, use the formula of the Vf squared is equal to the Vi squared minus 2g delta y. Wherein for the final velocity, that is 0 squared, or that is just simply 0, is equal to the initial velocity of 18 meter per second, then squared minus 2g. For our delta y, that is the final position of h minus the initial position of h over 4. Let's try to simplify this equation. This is 0 is equal to 18 meter per second, then squared minus 2g. For the h minus h over 4, this is the same as 1 minus 1/4, and then that is equal to 3/4 of h. And this is now 3/4 of h. And on this equation, we will solve for the maximum height. Let's try to simplify the equation wherein the negative 2g 3/4 of h transpose on the left side of the equation, wherein this is now the positive of 2g multiplied by the 3/4 of h is equal to the 18 meter per second, then squared. Solving for the h here algebraically, just simply cross multiply 4 on the right side of the equation and divide both sides by the 6g. And this will be a 18 meter per second, then squared, divided by the 6g. And take note, the 4 is being multiplied on the 18 squared, and this is divided by the 6g. And that 6g is the 6 multiplied by the 9.8 meter per second squared. Then solving for the maximum height now, just input this equation on your calculator. 4 multiplied by the 18 meter per second squared divided by the 6g, or the 6 times the 9.8 meter per second squared, and this will be equal to 22. Okay, 22.0408 meters. And this will be the maximum height of the object. And since we now have the maximum height for the object, we can now proceed in solving for the initial velocity, and that is the initial velocity Bi is equal to the square root of the 18 meter per second, then squared, plus the acceleration due to gravity of 9.8 meter per second squared, multiplied by the maximum height of 22.0408 meters, divided by the 2. Then, just type this equation on your calculator. Therefore, for the initial velocity of the object, this will now be equal to 20.7846, and of course for the unit, that is a meter per second. And this will be our final answer for the initial velocity of the stone. Okay, and that's it for our example problem number 2. Then, let's try to have another example problem. For our last example problem, this problem is a combination of having an acceleration of a, then after that, it will move under a pre-falling bodies. Wherein, for our problem, a rocket moves straight upward starting from rest with an acceleration of 29.4 meter per second squared. Let's try to illustrate this problem. Let's say that the rocket is at this position, which is our yi is equal to 0. Then, this rocket starts from rest. That means the initial velocity of the rocket is 0 meter per second, and it will accelerate with a acceleration of 29.4 meter per second squared, and this is brought by the fuel of the rocket. Then it runs out of fuel at the end of 4 seconds. That means after a time of 4 seconds, the rocket now will move under a pre-falling bodies, wherein the rocket, of course, it will still continues to coast upward, reaching a maximum height before falling back to Earth. Find the maximum height the rocket reaches. Let's say that after a time of 0.4 seconds, the rocket again will still continue to move upwards, and after reaching this maximum height, let's say that the maximum height is h, and it will now fall back to the earth. And for this problem, to solve for this maximum height h, we can divide it into two parts, wherein for the first part of the motion, this is having an acceleration of a, and for the second part of the motion, which is under a pre-falling bodies. Then, here, having an acceleration of a. This is our second part of the motion. Now, to solve for the maximum height h, first, let's solve for what will be the height of the rocket that it will reaches after a time of 4 seconds. Since we have here a constant acceleration of a, which is 29.4 meter per second squared, we can use the formula for the first part of the motion. On the first part of motion, we will use the formula of delta y is equal to the BIT plus the 1/2 AT squared. Take note that this is plus 1/2 AT squared because we will use the acceleration of the 29.4 meter per second squared. And for our delta y, this will be a final position. Let's say that at this point, after a 4 seconds, this is our YF, okay? And this will now be a YF minus the initial position of YI is equal to the VIT plus 1/2 AT squared. Solving for our YF here, this will be transpose the negative YI on the right side of the equation, and since that YI is just 0, therefore our final position for the first part of the motion, this will be equal to the initial velocity, which is equal to 0 times the time t, which is 4 seconds, that will give us 0, then plus 1/2 the acceleration of 29.4 meter per second squared multiplied by the time of 4 seconds then squared. Solving for our YF now, this will give us a value of 235.2 meters. That means the rocket will reach a height of 235.2 meters after a 4 seconds. And to analyze the part 2 of the motion, we need to determine what will be the velocity of the rocket after a time of 4 seconds, which is, that will be the initial velocity for the pre-fall here, wherein we will solve the VF for the first part of the motion, and this will be the initial velocity for the second part of the motion. To solve for the final velocity, we can solve it using the formula of BF is equal to BI plus AT. Again, this is a plus AT because we will use the acceleration of the rocket, that is a 29.4 meter per second squared. Solving for the final velocity now, the initial velocity is equal to 0, the acceleration of 29.4 meter per second squared multiplied by the time of 4 seconds. Solving for the final velocity now, this will be equal to the 117.4 0.6 meter per second. And this final velocity of the rocket will be the initial velocity of the rocket as the rocket will move under a pre-polling bodies. And using our equation for the pre-polling bodies, let's now proceed with our part 2 of the motion, wherein we can use the formula of the delta y, which is equal to the VIT minus the 1/2 GT squared, wherein for our delta y, again, that is YF minus YI is equal to the VIT minus the 1/2 GT squared. But take note, if we will use this equation, we need to find the value of the time for the object or for the rocket to reach the maximum height. And I suggest instead of using this equation, let's use the formula of the VF squared. Instead of using that, let's use the formula of VF squared is equal to the VI squared minus the 2G delta Y. Because if we reach the final position of the object as the maximum height, take note that the final velocity here is equal to 0. For YF is equal to H, this is our H max. The final velocity of the object or the rocket should be equal to 0. And for our initial position YI, take note that this is equal to the position of the 235.2 meters from the ground. Then, using this formula now, our final velocity is equal to 0. That is a 0 squared or just simply 0. The initial velocity of, which is the final velocity of the rocket for the first part of the motion, 117.6 meter per second, then squared, minus 2g. For our final position, this is the maximum height, capital H. And for our initial position, yi, that is equal to the 235.2 meters. And our goal here is to find this h, which is the maximum height. Solving for this equation algebraically, let's just simply transpose the negative 2gh minus the 235.2, and that is positive 2g, multiplied by the h minus the 235.2 meters is equal to the 117.6 meter per second squared. Then, just divide both sides of the equation by the 2g, which is the 2 times the 9.8 meter per second squared. Then, transpose this negative 235.2. Therefore, for the maximum height h now, this will be equal to the 117.6 meter per second, then squared. Then dividing both sides of the equation by 2g, that is a 2 times 9.8 meter per second squared. Then transposing the negative 235.2 meters, and that is a plus the 235.2 meters. And by that, therefore, the maximum height the rocket can reach will be equal to, let's input this equation on the calculator, and this is equal to the 940.8 meters. And take note that this height is measured from above the ground, and this is now a 940.8 meters above the launching point, or let's say above the ground. Or since the problem does not state that the rocket is from the ground, let's say that this is above the launching point. Above the launching point. And this will be our final answer now. 940.8 meters. And that's it for our discussion for the pre-polling bodies.